Hello everyone, welcome to lecture on formal specification and verification using Coq Proof Assistant. This lecture includes some proof of some lemmas and theorems based on natlist with some functions like alternate, concatenation, and many others. So far, this library less.v includes basics.v and induction.v. These libraries have already been compiled using Coq compiler, and after compilation they have been included here using require import command here, and then here are some definitions based on natlist, the definition of natlist type, and then some functions on natlist, and a number of lemmas defined with natlist. All of these lemmas and their proofs are here. So I'll just compile till the cursor point, and then I'll continue adding some more lemmas and theorems, and then completing their proofs. So here we have a theorem. This theorem is defined where the length in alternate functions, length, alternate, and the lemma, the theorem statement is for all L1 and L2. The type of L1 and L2 are not sometimes skipped because the Coq type inference facility allows us to skip the type of variable sometime, and because the type inference facility automatically determines or infers the type of these variables. So length, the statement is length of alternate L1, L2 is equal to length L1 plus length L2. So on the left hand side there is length of alternate L1 and L2, while on the right hand side it is equal to the length of L1 and L2. So that means that the alternate function doesn't change the lengths of the two lists L1 and L2. So if we combine the two lists L1 and L2 using alternate and then calculate their length, this is equal to calculating the lengths of L1 and L2 separately and then adding the two lengths. So let me compile its statement. The statement of this theorem is okay. We can now enter into the proof mode of the Coq. So the first actor that I'm going to use is introduction, intros. This will introduce these two variables L1 and L2 above the line into hypothesis. So L1 and L2 are now above the line and the hypothesis. As usual, we can continue using case analysis on the construction of either of the two variables L1 and L2 because they are inductive variables. So using case analysis we can proceed. We can choose to do induction on either of the variables, but we normally proceed with induction on the first variable, that is L1. So induction on L1, and obviously this will give us two subgoals. So we got two subgoals. With to focus on the first subgoal we use the plus notation or the plus operator. So the second subgoal disappears for the time being and will reappear after we close the first goal or the first case, which is the base case normally when L1 is null. So if we do not know how to proceed, then we can simplify. Normally the first case, which is the base case, can be closed using simplification. So if we simplify the functions, Obviously, this alternate function has the first argument is null, so it will be simplified. Also, this length has a null list, so it should also be simplified. But let me see and let me compile it. Okay, so we got this is simplified to 0, and this 0 plus some number is simplified to this some number, and this is alternate empty null, and L2 is reduced to L2, so we get length of L2 and length of L2 on both sides, and this can be closed easily using the auto tactic. Okay, now we can focus on the second subgoal, and again we are in a situation where we have an inductive hypothesis here, and we have L1, which is the second case of L1, where L1 is non-null. So we have now solved the possibility that L1 would be null. That has been now solved, and now we are in a situation where L1 is non-null, non-empty. So we can we have already proved a similar theorem or lemma already. So now we can proceed with the case analysis on L2. In a similar theorem, we used induction on L2, but we can also try destruct on L2. Maybe we do not need an inductive hypothesis. In the earlier case, we didn't need the inductive hypothesis related to L2. But we were able to close the theorem using the inductive hypothesis on L1. So in that case, destruct is also sufficient if we do not need the inductive hypothesis on L2. So we can use a case analysis on of L2 using destruct. We can also use the same induction hypothesis, but I'm going to practice on destruct on L2. To see that maybe the inductive hypothesis on L2 is not required, but we should continue with case analysis on L2, and we have two tactics for that, either using destruct or either using induction. So let me continue with destructing L2. So in this case, also we would get two subgoals, and one L2 would be null. L2 is null, and the other L2 would be non-null. So we got two subgoals, and to focus on the first subgoal, I'm using the symbol minus symbol. So now the focus is on the first subgoal where L2 is null. So as usual, we should proceed with simplification so that the terms are reduced, and then we can see if we can rewrite either any existing theorem or lemma, or if we can rewrite the inductive hypothesis. Let me simplify it. After simplification, we got this, and we should now look for existing lemmas or theorems, or we can rewrite the inductive hypothesis that we have already. Inductive hypothesis on list L1, inductive hypothesis L1. We cannot rewrite it because we have alternate in the hypothesis, so we are not in a good position to rewrite inductive hypothesis that we have in the hypothesis. But we have some functions, some lemmas already proven. For example, let me print plus n o. So n plus o, where n is a natural number, o is 0. So we already have a situation like this here. So this is an n, this is an o, 0. So some n plus o is equal to n, and here n is length L1, which is a natural number. So this plus operator should return length L1, where on the right hand side we have 0 and on the left hand side we have n. We cannot simplify it because the plus operator is here. So when the left argument is 0, that can be simplified because it is defined in the plus definition. But when on the right side the argument is 0, this is not defined in the function. So instead there was a lemma proved that showed that if the right side argument is 0, then that is equal to the left argument. So here we have the function n plus 0 is n. 0 plus n is equal to n as well. That can be simplified, but we have a lemma for n plus 0 is equal to n. So we can rewrite the plus no lemma. So plus rewrite plus underscore n underscore o. So this lemma, with the help of this lemma, we would be able to replace this term with length L1. Yes, we can replace it. Length L1, we got length L1. So on both sides we got similar terms. So we are now able to close it with auto tech. And with this we can now focus on the second subgoal of the second subgoal. So we are in this subgoal, and in this subgoal we got two subgoals using destruct L2, and we are now in the second subgoal. Okay, so we can simplify it if we do not see how to rewrite or to apply any existing lemma or theorem, then we can proceed with simplification. Let me simplify it. So it simplifies to this expression or this subgoal, and here we can also use simplify in all to see if anything happens in the hypothesis. Simplify in all, so if we can see if anything happens here. Yes, some the expression in the inductive hypothesis also reduced, so this may be helpful. So let me continue with this. Okay, so can we proceed? Here we have length L, S up length L2, and okay, so we have a lemma here that we had admitted. Length alternate append, length alternate append, length alternate append. Can we rewrite this lemma? Okay, let me first try to change the order of this plus operator, length L1 and successor of length L2. I just want to change the order of this. Rewrite plus commutative. Okay, so the order we just here, because we have two successors here and one successor is here and one successor is internal to the parenthesis. I just want this successor to be to bring it here, but for that I need to swap this term with this term, and this is allowed by the commutative property of plus. So I use rewrite commutative property with plus, so I brought it as here. So the terms are a bit similar and look. Now I rewrite the length alternate append tactic lemma that we have here. So length alternate and then two lists. So length alternate and then two lists here. I just rewrite it here. So I copy this lemma and then use rewrite tactic to rewrite it. Rewrite, and this will rewrite it should rewrite this term. Let me try it. Okay, found no subterm. Where is the problem? Okay, so we cannot write in the existing situation, we cannot rewrite this lemma, but we can rewrite another lemma, the statement of which is like this: add successor L. Let me print this lemma and then we can see. So it's like here, successor of n plus successor of n plus m is equal to successor of n plus m. So here we have successor of this, which is successor is outside the parenthesis, and here we have successor of this, where n is like length of L2 is n here, plus then we have m here. So to change, to enclose this length L2 and length L1 and combined in parentheses, and to keep this s outside the parentheses that combines this L2 length L2 and length L1, then we can use this lemma, add successor L. So let me rewrite it. Rewrite add successor L. Yes, it changes it to this situation. Now let me rewrite this theorem and we can see what happens. Okay, so I just compile it. Again, it gives an error. I think the problem is that we have to rewrite it in the opposite direction. Why? Because here we have this n is not here. We have alternate here, but here we have alternate L1 in L2, while here we have alternate L1 and L2. But on the right hand side we have a situation like this: successor of length alternate L1 L2, length successor length alternate L1 L2. This is a term which is exactly equal to the right hand side. So we can get a term like this when we rewrite length alternate right from right to left. If we rewrite it from length alternate right, if we rewrite it from right to left, then we would be able to replace this term with a term similar to this one, a term similar to this one. So let me rewrite it from right to left. Found no subterm. Again, we have the same problem. So where is the problem? Okay, so then length alternate right is not the correct lemma to rewrite here, and instead if we look here to this theorem, length alternate append, I think this should be able to, because we have no n here we have no n, so we cannot rewrite it. But let me try this: length alternate append, and the situation is exactly like this. Length alternate L1 L2. Yes, we should be able to write it. So let me replace this with append instead. Okay, so good, we can proceed now. And now we have lemma for append length. Let me print that. In fact, we have just proven that append length. Let me see that if we have that lemma. Here. So we have a situation like here. Length L1 plus L2. Length L1 plus L2. So we can replace this with length L1 plus length L2, and that would give us exactly this situation. It would not be exactly this situation, but we can then change it with commutative property. So append length L would replace this length L1 plus L2 with length of L1 plus length of L2. So let me rewrite that. Rewrite length append underscore length. Okay, so we got length L1 plus length L2, but here we have length L2 is first and length L1 is second, but the order is different. So we cannot just close it with, I think we should not be able to close it with auto, because yes, we cannot close it. So instead we have to continue using commutative property. So rewrite plus commutative, because that is what plus commutative tells us. Plus commutative can be applied here, but this will change the order of the first plus function, and it is okay with us. So let me write it. Yes, so it changes the order of the first plus function, and now we are able to close it with auto, because both functions are the same. Both expressions on the left hand side and right hand side are exactly the same. I think we have made a mistake here, and if we do not use this plus commutative property, then I think we would not need this plus commutative property again. Let me just skip to this point, and I just okay. No, then we would not be able to apply this. So applying this or rewriting this plus commutative is good at this stage, and then we need to use plus commutative again here. Okay, so this proof is complete now, and we just close this proof with QED. Okay, so this proof of this theorem required a number of other lemmas and theorems here, plus NO, plus commutative, add successor L, length alternate append length, and commutative property, and then at the end we were able to close this theorem. Okay, so another theorem reverse append distributor for all L1 and L2. Reverse of L1 concatenated appended with L2 is equal to reversing L2 plus reversing L1. Okay, so let me enter into the probe mode. Okay, so what this theorem basically says that if the two L1 and L2 are concatenated or appended with each other and they are reversed, this is equivalent to reversing the two list independently or individually or separately, and then appending the two reversed versions, the reversed versions of L1 and L2. Remember that we have also changed the order of L1 and L2. Here L1 is first, here L2 is first. So Okay, we should be able to close this proof. Okay, so intros, and then intros, and then let me perform induction on L1. Induction on L1 to see the cases of L1. Two cases. Focus on the first case, first goal. Simplification should work. Simplified. We were not able to make both sides exactly the same, because here the plus concatenation here the plus operator is used here, so this is append. The first argument of the append is null, so it was reduced to L2 because it is there in the definition of the append function. But here this reverse is reduced to null because reverse of null is null, but this plus operator is not reduced because the right argument is null. So so this is not reduced, but we have a theorem or lemma, append null right, where we have proved that if the right list is null, then it can also be reduced to the other list. So rewrite append null right. We can reduce this when this is a theorem or lemma that states that if the right argument is null, then it can also be reduced to the left argument. Okay, so now we can close this with just auto, and then we can focus on the second subgoal. And in the second subgoal, as usual, we can proceed with the simplification. If we simplification is not mandatory, if we can reduce, if we can rewrite the inductive hypothesis or any other lemma or theorem in the existing shape, then we should proceed with that. But if we do not remember, or if we do not know if we can rewrite any existing theorem or lemma or the inductive hypothesis, then we should proceed with simplification. Okay, so simplification gave us a similar or a familiar shape, and now we have reverse of L1 plus L2, reverse of L1 plus L2. This can be replaced with reverse of L2 and reverse of L1. So let me rewrite inductive hypothesis, rewrite inductive hypothesis on L1, and this replaces this term, and this replaces this term with this term, because this left hand side is exactly equal to this expression. Okay, so we reduced it, and I think now we both left hand side and right hand side are exactly the same, or not. Let me see. Oh no, because we have parentheses here. So we have parentheses here, but there are no parentheses here. But this parenthesis can be removed using the associative property on append. Rewrite append associative. We have already proved this. If you do not remember, just I will use print append associative. So let me see that what this associative property says. That this associative property says that for any three list, if there is a parenthesis on the left hand side, it can be removed. There, the parenthesis is not there. So we can just remove the parenthesis here. So we remove the parenthesis. Now we should be able to close it with auto. Yes, no more subgoal. Okay, so we can also prove the involutive property for the reverse, and the involution property says that involutive, that for any list L, if we apply the reverse twice, we will get the same list again. It is just like complementing a Boolean variable twice gives the same variable. So this reverse will reverse the order of this list, but this reverse will get the original order of the list, and that is equal to the same L. Okay, so this property is called involution property. Okay, so we get into the proof mode, and here intro. So it will introduce L into the hypothesis, and we can use induction on the only one variable, and that is L. We can also use induction with as prefix or as directive. So the first goal has no new variable or hypothesis. The second goal has a variable. So let one natural number. Let me call that natural number n prime, and there is a tail. Let me call that tail L prime, and there is an inductive hypothesis. So let me call that inductive hypothesis a reverse hypothesis. So these three variables would be introduced. The first subgoal plus auto. So what the auto would do is that reverse has been defined if the only argument is null, then it returns null, and then this reverse would get a null argument, so it is again reduced to null. So null would be achieved on both sides, and even auto does this in one go, but we can simplify it first and then we can reduce it, we can solve it. So but if we directly use auto, then that is also sufficient. Okay, now we can focus on the second subgoal, and we would get an inductive hypothesis. Remember that the name of this inductive hypothesis is what exactly we have chosen for it. Okay, so we can now continue with simplification to simplify this expression. Okay, so this expression has been simplified. Reverse of n prime plus double colon L prime is reduced to reverse of L prime plus n. This n is a list, but with single element. Okay, so what we can do now, we have just proven a theorem that is distributor, reverse append distributor. So this reverse applied inside is equal to reverse L prime and then a reverse of this. So you would get this, like we can reverse of L1 plus L2 is equal to reverse of L2 plus reverse of L. That means that we can internally apply the same function over the two lists separately. So here we also have two lists but appended with each other. So this applying reverse append distributor theorem would reduce this expression to reverse of L prime plus reverse of this list. Okay, so let me rewrite it. Okay, so we have get that, and the order is also changed because we have a changed order, reverse of L2 and reverse of L1. So that's why we get reverse of L1 on the right hand side of this plus operator. Okay, but we can now rewrite the inductive hypothesis at least, because we have reverse of L prime is equal to L prime and reverse of L prime, so we can get L prime here. So just rewrite the inductive hypothesis IHREV. Okay, so we get reverse of N prime plus L prime. We can I think we should simplify it, and this simplification would give us, because this is a list of only one element, so reversing this would give us the same list. So simplify it. Okay, so we got both sides equal, and we should be able to close it with auto. No more subgoals. We are done. Okay, so we have just proved that reverse function is involutive, and we can continue with associative property of append. We have already proved associative property with append, but now I define a theorem that has 4 lists. So append associative, but 4 lists for all L1, L2, L3, L4, L1 plus plus, L2 plus plus, L3 plus plus, L4. So we have 2 levels of parentheses, and this is equal to L1 plus plus L2 plus plus L3 plus plus L4. Okay, so L1, L2, L3, L4, the order is the same, but the order of parentheses is different. So here the parentheses are on the right side, here the parentheses are on the left side, and that is what associative property tells us. Okay, so proof. Intros, so it will just introduce the variables into the hypothesis. Okay, and we have the append associative property. So print append associative property. So let me print that associative property to tell us. Okay, so for any 3 list, the parentheses can be removed. So the parentheses are on the left hand side. This is equal to adding the parentheses on the right side, but the parentheses on the right side are not visible because the plus operator, the notation for the plus operator has been defined as right associative, so that's why they're not there. Okay, so we can rewrite this append associative theorem or lemma. Okay, so rewrite append associative, so we can rewrite it. Okay, so this changes or this removes the right parentheses are not visible, but the left parentheses are here. So we have to remove these parentheses from here. And when we rewrite append associative, it removes the first external parenthesis. And if we rewrite this the same, take the same lemma again, it will remove the second parenthesis as a second pair of parentheses as well. And now we got the same terms on the left hand side and right hand side. We are able now to close it. Okay, so we we rewrote append associative 2 times. We could do this in one step as well, like do to rewrite append associative. So this will do to rewrite. This tactic will perform 2 rewrites for the append using append associative lemma, and this is equivalent to writing these 2 lemmas separately. So I will just enclose this in parentheses. I will just enclose or comment this out so that you remember that what this do to rewrite append associative does. And now we have no more subgoals. We are done with this theorem as well. Thank you.